Good afternoon, everyone. I welcome everyone for the More Profit for Nitrogen special session. So, why we are having this special session? So, this is a 5-year program funded by Rural R&D for Profit program across cotton, dairy, sugar, and horticulture industries. There were 11 projects, 77 research staff and technical staff, 45 trial sites supported by labs, small plots, and modeling from Hobart to Darwin. So, there is pretty intensive science going on in this project. I hope you all enjoy that. So now, in the interest of keeping time, if the presenters are going more than 12 minutes, you will lose the opportunity for interaction during question time. I will try to maintain the time. Now I invite Helen Suter, who is our first presenter, to talk on improving dairy farm NUE using advanced technologies. Welcome, Helen.
Thanks, Gunnar. Do I have to wait for this to become 0? Huh? No? Oh, okay, great. All right. So, as Gunnar said, this is a project we've had in the More Profit from Nitrogen program, improving dairy farm NUE using advanced technologies, but I won't be talking about the advanced technologies today. And I'd just like to point out that this project is supported by funding from the Australian Government Department of Agriculture, Water and Environment, and Dairy Australia and the University of Melbourne. So today I'm going to look at just one component of this project, and the title of the talk is Valuing Soil Organic Matter for Effective Nutrient Management in High Input Dairy Pastures. Just acknowledge my co-authors Oksana Belyeva, Graham Ward and Delhi Chen. So just as a bit of a background, so in dairy systems down in Victoria under irrigation, you can have these very high inputs of more than 400 kilograms of nitrogen per hectare. And apparently we see that there's a poor nitrogen use efficiency, so maybe 40 to 50% efficiency and utilisation of that nitrogen. These systems have high carbon, so their carbon levels will be around 3 to 4% and even higher in the topsoil, and so that indicates that there's potentially a large nitrogen store that could be utilised. So the research question that I'm going to look at here is, where does pasture nitrogen come from, and does this depend on the soil, and how can we how do nitrogen management decisions affect the sustainability of our pasture production systems into the long term? So here's the experimental design. So in this part of the program, I had 6 soils that were in typical soils for the region, came from a number of different sites listed there, and we collected these soils in these PVC cores to do 15N labelled studies on them. So we brought the cores from those other sites into our main field site and established them in 3 replicates under irrigation in these types of rows set up here. So the soils were largely acidic, mostly, and they had, as I said, the carbon levels range from 2.8 up to 8.8 for one of them. This is averaged over the 0 to 20 centimetres of the core. They're all quite sandy because it's a coastal sort of located region, so it's down near Warrnambool for people who know Victoria, in southwestern Victoria, in our high rainfall zone, which is about 800 millimetres, and they had variable CECs as well, these soils. So we established these cores in the site on the 16th of April 2019. We extracted the cores on the 20th of June, and we did 2 harvest cuts over that time that was indicative of a grazing cycle. We applied 40 kilograms of N per hectare as 15N labelled nitrogen, which was the standard practice for the region. And it was under irrigation with those 3 replicates, as I talked about. You'll notice more cores in there. Some of those cores were from other projects that we were running. So looking at the results, the first table I'm going to show you is looking at the 15N recovery in the plant, so the percentage recovery at the 2 harvests and total for that harvest. And the first harvest was cut 21 days after fertiliser was applied. The second harvest is 65 days after fertiliser was applied. So normal practice would be to fertilise after every grazing cycle, but we haven't done that in this experiment. So if we look at our nitrogen recovered, we find that they're quite similar levels between the first and the second harvest. Normally we would pick up a better recovery in the first harvest, and it would progressively decline over time as we cut that pasture. The levels that we're getting, ranging from 13 to about 25% in that first harvest, similar levels in the second harvest. These levels would be typical of what we would pick up in a first harvest cut. So totally we're getting between 32 and 43%, and in terms of differences between soils, we only picked up a statistically significant difference between the very low one and the very high one, the low and high recovery there. We also looked at what was recovered in the soil, and so we're picking up about 20 to 34% is being recovered in the soil. So even though normally we might think we're not getting much recovery in the plant and it's being lost, it's actually being retained by the soil, which is becoming more well known. So when we look at our total recovery and total losses, we can see that our losses are ranging from 30 to 45%, and so our recoveries are 55 to 70% recovery. So we are having quite a bit of loss from this system. The nitrogen was applied in autumn, so it's possible that it's volatilised, it could have leached, it could have been denitrified. We haven't quantified any of those loss pathways. Looking at the nitrogen that's taken up by the plant, we found that we had, if we're looking at the first harvest, we've got less than the nitrogen that we applied, so that's a good sign. We're not sort of mining the system. If we look at the second harvest, that is also taking out an amount of nitrogen even though we're not applying it. So if we didn't apply more nitrogen, we'd start to mine the soil nitrogen. So we've got more coming out than we've actually applied. So up to 63 or 64 kilograms of nitrogen coming out from that 40 kilograms of nitrogen application. This is an extended table, so we've already looked at the 3 columns on the left there. The other thing we were interested in is where does the nitrogen that's taken up by the pasture come from? Is it coming from the fertiliser or is it coming from the soil? Because I talked about that big organic matter pool that was available. So if we look at the first harvest cut, so this is the harvest that's grown immediately following our fertiliser application, we found that even in this condition, 77% of the nitrogen or more that the pasture is taking up is coming from that soil nitrogen reserve. So the fertiliser is added in, but we're getting nitrogen also coming out of that mineral nitrogen pool available. And as expected in the second harvest, because we didn't apply any more nitrogen, we're getting a lot more that's coming out of that mineral nitrogen pool and not utilising that nitrogen that was applied in that first fertiliser event. And these values are typical of what we've seen in many systems that we've tested. I had a look at whether the soil properties influenced what we found. So I looked at the soil properties in terms of the recovery in the plant. And we found significant differences, but not very good relationships for soil pH. Similarly for organic carbon levels, and similarly for clay. So we are getting these significant relationships, but they're not very strong relationships. The strongest one is probably this CEC, which is a combination of the effect of the organic carbon and the clay content in that soil. We didn't do any clay mineralogy assessments of the soil at all. If we look at the influence of soil recovery on of soil properties on the total nitrogen recovery, so that's the recovery in the plant and in the soil, again we do find significant effects. The significance is less now of these factors of soil pH, a poor relationship with the soil organic carbon. We have quite, I'm going to say stronger relationship, but it's still not very good, but a significant effect there. And not so with the clay, and then a similar level with the CEC, as you'd expect that to be similar with the organic carbon contents, and a slightly better relationship. So sort of, I guess the idea would be that with that organic carbon component, you would have, I guess that might take in the fertiliser that we're applying and hold that on, but retain it in the soil and it wouldn't get lost from the system. So I've got my conclusions coming up, so I'm nicely on time there, Gunnar. So what we found was 30 to 45% of the applied nitrogen was lost from the soil plant system. 32 to 42% of that applied nitrogen was recovered in the plant over 2 growth cycles. If we'd run this experiment out longer, we would expect to keep picking up that nitrogen, and we've measured in other sites over 12 months periods. You do keep picking up a little bit of nitrogen over time. In this case, we got a similar result in both harvests, and I think I didn't mention that our second harvest at this site had much higher biomass. So I think that's why we saw a similarity in the responses of the 2 harvests, was because we had more production at the second cut, which may have been issues of establishing the sites potentially. Over that 2 months, we removed up to between 42 and 64 kilograms of nitrogen per hectare, and the maximum in one harvest was around about the recommended application rate and the rate that we had actually applied to the soil. Interestingly, and this is what we're interested to focus on, is the amount that is provided by the soil mineral nitrogen, the soil organic matter pool. And so even when we've got that readily available nitrogen, we're still getting a lot that's coming from the soil. These soil properties that we tested did influence uptake, but they didn't actually influence how much came from the fertiliser and how much came from the soil, because I thought that would. If you had a lot more organic carbon, you might get more supply from the soil, but there was no relationship there. So my take-home messages: soil is supplying a large amount of the pasture nutrition in these dairy pasture systems. The contribution from the soil seems to be independent of the soil types that we've tested, so I would emphasise that we are in a particular area. So we've got sort of similar management systems, but we did have a range of organic carbon contents. I'm going to say that N recovery was related to soil organic carbon, even though I realised that relationship was not very strong. And what we're finding now is that if you apply fertiliser, it's not utilised very well immediately from the fertiliser, but it's very important for that fertiliser to be building the soil organic matter pool. So we don't want to recommend that be dropped excessively, because then we're going to start mining the soil nitrogen from that organic matter pool. And I shall finish up there. Thank you.
Thanks, Helen. There is no online question so far. Anyone else here has a question? Yeah. Go for it.
Thanks for your presentation. How is the distribution of fertilizer nitrogen across the soil profile?
The question is, how is the distribution of nitrogen over the profile?
So in these soils, we've just measured 0 to 20 centimetres, and we've sort of separated it in 2 halves. We do find the majority of it sitting up in that top part of the profile. And in sites where we've gone deeper, where we've had in situ soil cores, you're definitely picking up most of that in that top part where we've got the higher levels of organic matter and the root biomass that's holding that in. Yeah.
Is the fertiliser applied in granular form, or is a liquid spread over the core?
The question is, was the fertiliser applied in granular form or as a liquid? So this was a 15N labelled granule applied into these ones, yeah. But it was irrigated, under irrigation, but I'm not quite sure what time the irrigator came around. Because in another study on the site, where we had soil cores placed into the actual site rather than being brought in, we did pick up low recoveries under our dryland systems on an application in autumn, so we're assuming that there would have been a bit of ammonia volatilisation happening at that time. Yeah.
Any more questions? Okay.
Have you measured ammonia volatilisation on soil with pH 4?
Can you repeat the question?
The question is, have I measured ammonia volatilisation on a soil with a pH of 4? No, I haven't. Probably the lowest pH has been somewhere in the 6s that we've measured it. But in the with the way the pasture is growing, depending on the growth of the pasture, the urea actually may not even get to the soil because it gets caught up in the top of the pasture, and that's where the urease is. So the amount that you would get would sort of depend on where the fertiliser falls, how quickly it's hydrolysed, because then you get that little hot spot, and how much moisture is in the system when the fertiliser is being applied. So, but no, I haven't measured that.
Thanks, Helen. Yeah, I think we are close to time. Great talk. Thank you. Our next talk is virtual by Johannes Freud. Okay. Thank you. So that talk is also going to be on dairy industry, on nitrous oxide emissions from nitrogen management.
Hello everyone, my name is Johannes Friedl, and today I will be talking about N2O losses from urine patches following the application of DMPP-coated urea on dairy pastures. Our project was part of the More Profit for Nitrogen program, which was supported by the Australian Government Department of Agriculture, Water and Environment as part of their Rural R&D for Profit program. It was also supported by Dairy Australia. I've worked in this project together with David Rawlings, who was leading the project, and we had a couple of different sites in Kent. We did experiments in Kempton and in Casino, but also on a few satellite sites in northern New South Wales and down south. So urine is one of the main inputs of nitrogen, reactive nitrogen, to intensively manage dairy pastures. And when basically urine is deposited, we have a series of different biological, chemical, and also physical reactions in the soil, which lead to the formation of nitrous oxide, which is a powerful greenhouse gas and the single most depleting substance of stratospheric ozone, so environmentally quite harmful. We know that in these pastures, we have also other nitrogen inputs, such as fertilizer, and we import nitrogen with feed, and only a small amount, around 22%, is actually exported as milk. So that leaves a large surplus, and a large surplus for nitrogen losses from these pastures. What happens actually when urine is deposited? First of all, we can have ammonia volatilization straight away, but usually urine is rather quickly converted, hydrolyzed, and we have into ammonia. And the ammonia in the soil in solution is in a pH-dependent equilibrium with ammonium, which can be bound on exchanges, cation exchanges and organic matter in the soil. It's also in equilibrium with gaseous ammonia, and we can have gaseous ammonia losses, which then can lead to indirect N2O emissions from dairy pastures. The aqueous ammonia remaining in solution can be nitrified to nitrite and to nitrate, and both nitrite and nitrate are source pools for the production of N2O. And given the right conditions, when urine is deposited, we know that this can lead to rather high N2O emissions. So we have hotspots within the pasture that actually lead to N2O emissions. This is some data from the ryegrass season in Casino, and we can see that short time after application of urine, we already see relatively high emissions, up to 400 grams of N equivalent per hectare. The use of nitrification inhibitors reduces nitrification, as the name suggests. We've done a lot of work with the nitrification inhibitor DMPP, and DMPP and the product urea-coated DMPP is usually commercially sold as NTEC. So DMPP inhibits the first step of nitrification, and we know from the literature that this should actually reduce our source poles of nitrite and nitrate. And in some work we've done, we actually showed that. We measured gross nitrification, and we could reduce gross nitrification considerably. And that translated to a reduction in cumulative N2O losses. But our experiments so far have mainly focused on fertilizer-derived N2O losses. And in this experiment, in this study, we wanted to have a closer look at N2O emissions from the urine patches. The site is in Casino, northern New South Wales. It's a heavy black vertisol, about 3% of carbon, and a pH of 6.3%. It's part of the subtropical dairy industry, which accounts for 6% of the national production. And we have here ryegrass kikuyu rotation, fertilization up to 8 times per season, 35 to 50 kg. And even though application rates vary widely, you can say that around 200 to 400 kgs of N are applied per hectare per year. Livestock urine is known to be major input, as I said, and these urine patches can have a nitrogen loading equivalent of around 800 kg of N per hectare. Livestock urine accounts for 50% of the Australian N2O emissions, and the tier 2 emission factor is 0.4%. The IPCC default value in comparison is 2%. So in the inventory, we account for fertilizer and urine via emission factor separately, and that assumes no interaction. So that the increase, basically, if you apply both fertilizer and urine, that you just get the added amount. But that actually hasn't been tested, and that could lead to either double dipping or an underestimation if we have actually a priming effect. So there has been a lot of studies of treating urine patches directly, identifying urine patches with remote sensing, and then targeting these patches in particular. But what we wanted to look here is at actually a simple strategy, because urea is applied anyways, and so we wanted to look at the DMPP, the effect of surface spread DMPP coated urea on N2O losses from urine patches. We know, and there's a talk of Dave later this afternoon, that DMPP coated urea has agronomic benefits, and we wanted to see whether we could combine this also with a reduction in N2O losses. Here's our experimental setup. We had 4 different treatments, and the experiment was conducted in summer, December 2017 till April. In Kikuyu, we had 4 treatments: urea only, urine only, and then the combinations urea plus urine, and then DMPP coated urea intake plus urine. We had, over the experiment, we had 3 applications of fertilizer amounting to more than 100 kg of N per hectare. We simulated the urination event with 2.5 liter urine on the basis of our auto chamber systems. That's a quarter of a square meter, and the loading was equivalent to 750 kgs of N per hectare. We used our automated greenhouse gas system and also measured some additional parameters such as pasture growth, soil oxygen, soil water, DOC, and soil mineral nitrogen. And here are some results. We see the temporal variability of nitrate and ammonium in these different treatments. And the takeaway message here is that we do see a response of urine application. And we see this large spike in all urine-containing treatments in the ammonium pool. But apart from that, we actually do not see much of a difference in mineral N. This is what we've seen this before, looking into gases N losses from pastures, that the soil mineral N pools usually don't give us a clue about the actual substrate availability for gases N losses. What we also saw, and that was quite interesting, is we saw high diurnal variability of N2O fluxes. And we basically saw an inverse relationship with temperature. So at the hottest time of the day, highest soil temperature between 2 and 4 in the afternoon, we had lowest oxygen levels in the soil. And that surprisingly led to a decrease in N2O. We speculated a bit, and we're not quite sure, but it may be explained by increased reduction of N2O to N2. What's important though is that you really need subdiurnal resolution measurements of N2O, otherwise your daily average will be quite off. And here are the treatment results. We can see that lowest emissions were from fertilized treatment with urea only. And it actually wasn't, that was relatively high. So you could also see that before in the soil mineral N availability, soil nitrate was relatively high in the urea already. And so we do not see a significant difference between urea and urine. But urea and urine significantly increased N2O emissions compared to urine. And this effect was reduced, or this effect was limited by the application of urine together with NTEC. So we have quite a interesting treatment effect here. We see that a linear effect, and that's also reflected in the emission factors. We have a linear interaction between fertilizer and urine. So if you apply fertilizer to a urine patch, you have a linear increase, but you can reduce this increase by using NTEC urea. Fertilizer emission factor during that period of time was relatively high. And using the default value is likely to lead to an underestimation of N2O losses during that period of time. But as I said, it's just a short snapshot, and we can't make too many assumptions from this short period of time. But what we can say about fertilizer losses, but what we can say is that the sole urine emission factor was a bit lower than the default value of 0.4, and so the urine emission factor may overestimate N2O losses. So coming to the conclusion, we can within our experiment, but also from previous experiment, we can say that N2O emissions from urine patches just in casino alone are highly variable, and to get a robust estimate of an emission factor, we need longer term studies to basically consolidate that data set. The subdiurnal variability of N2O fluxes means that for a robust EF estimate, we really need high temporal resolution measurements. We could show that there's a linear effect of nitrogen fertilizer application on urine patches. So if you go and apply urea on your urine patches, you see an increase. there is no added effect, but it's a linear effect. And if anti-urea is applied, we can reduce this effect back to urine alone. So this means we have quite a simple method or a simple way of reducing fertilizer-derived N2O emissions in combination with N2O patches. And this is much more easily to integrate within farmers' practice, as the only thing that needs to change is the fertilizer product. So we can say that if using DMPP fertilizer, there's no added benefit of avoiding fertilization of urine patches. And I would like to thank everyone. This talk was actually from Dave Rawlings. Here I thank myself, but also Dave for leading that project. For all those who participated, including Evi, who did part of a PhD with us, Magella, Sarah, Julie, and various other interns and students, New South Wales DPI, Warwick and Michael, and first and foremost, Wayne and Vicky Clark for letting us do all the work at their farm and supporting us, and Bill Ferguson. And if you're interested in more information, please visit the link above. Thank you.
Yeah, thank you. All right. Good afternoon, everyone, and thank you for attending this session. My name is Dio Antile, and I'm going to present a summary of the work that we conducted for the more professional nitrogen, looking at the development of nitrogen use efficiency indicators for the Australian cotton, sugar, dairy, and horticulture industries. This work was funded by the Department of Agriculture, Water and Environment and CRDC, and it's been conducted with the assistance of Associate Professor Phil Moody and myself. So the objectives of the work were to address the lack of harmonization of nitrogen use efficiency terminology and definitions that was evident in Australia. And this came up from the work that we did in the more professional nitrogen, that we identified a need to standardize the terminology used for reporting NEOE. So the work was conducted by reviewing current metrics used both in Australia and overseas that reflect productivity, profitability, and environmental aspects of nitrogen management. We collated data from the program and then used those indicators to calculate the NEOE metrics. And then we identified what were the suitable a range of NEOE indicators that were relevant for Australia specifically to communicate cross-sector research findings from the program. So we identified or shortlisted 5 indicators that they reflect different productivity, profitability, and environmental aspects of nitrogen management, as you can see on the screen. Those are the 5 indicators that we selected, and we provide the definitions in the paper I'm going to show in a minute. So importantly, so this table is a bit busy, but importantly, the different indicators will have a different focus, and therefore they will have a different cross-industry usefulness. We identify those, and they are reported in the paper. And for example, if I take, so this is what I'm saying, that they have different focus and different applicability for different industries. and the practitioner will have to select which one of those indicators is more applicable to a specific situation. But for example, if I take the partial factor productivity of applied nitrogen, it'd be useful, for example, to benchmark cropping systems NUE in terms of harvested product produced per unit of fertilizer applied. But it's confounded by the fact that the contribution of background soil nitrogen to yield is not considered. So in our review, we found that the recovery of fertilizer across the industry was highly variable and very dependent on the cropping system and the specific conditions on where that study was taken. Typically, the range varied between about 30% and 75% recovery in the harvested product. The contribution to crop nitrogen uptake from soil nitrogen and the in-season mineralization was also variable. And we identified that in order to accurately report NUE, the use of a zero treatment in any NUE study is quite important. The average marginal return from urea ranged from somewhere around $3 to $12 per kilogram of nitrogen applied, taking the price of nitrogen at $1.5 per kilogram. So from there, we conclude that there's no economic driver to reduce nitrogen inputs in most cropping systems. And we put the question up there to suggest that there should be perhaps incentive schemes linked to improve nitrogen use efficiency in order to reduce environmental risk. We also presented this framework that is taken from the International Nitrogen Initiatives. And we use the example of cotton to highlight, based on data that is being already published, what would be perhaps the target NUE, which is not a single value, but rather a range. And we presented this conceptual framework to suggest that there is a range of NUE that we should be working towards. And what reflects in the middle line there, the Rochester minimum NUE, is what reflects the best management practice. So if we were over the maximum NUE range that is shown on the image, then that suggests that the NUE is too high for the system and would be probably mining some nitrogen. If we are below that range, the NUE is too low, and we are obviously losing. There's a loss of profitability there because nitrogen is also lost to the environment and not efficiently used. So that system has to be validated, and is what we are doing now in the follow-up case studies, working in collaboration with Econ. So these results are all published now, and I invite you to consult the paper where there's more details on the specifics for each indicator. And in the paper, there's also supplementary data provided because some of the industry have very specific NUE indicators that are also useful, and they can be consulted in the paper. So yeah, so thank you very much to our sponsors, our collaborators in the project partners, Marguerite White, and also I like to acknowledge my former colleague, Phil Moody, who passed last year, but he was instrumental in implementing this program. Thank you very much. Thank you very much.
Thank you, Gunnar, and I don't know if my talk has loaded up yet. That's all right. I can probably get started. I'm just going to apologise up front. Some of you in the audience are not going to like what I've got to say today. And if I get some heckling and some jeering from the audience, that's perfectly fine. I actually do have quite a thick skin. Again, like the previous talks, several acknowledgements, and in particular would like to acknowledge Sugar Research Australia here. Lots of collaborators on this project, the team from DPI, Southern Cross University, Sunshine Sugar. In particular, would like to acknowledge our partner sugarcane farmers. They've all been extremely generous in their field trial, or giving us access to the field trial sites. And also Kirsten Verberg and Daniel Cozzolino. I think a lot of our data is going to end up with those guys, and they're going to help us to sanitise it into more useful industry outcomes. So ultimately, the objective for the work is around increasing nitrogen fertiliser use efficiency and also sugarcane productivity. And essentially, in a nutshell, what we're trying to do there is, and it goes a little bit to some of the questions that Helen had before, understanding how much nitrogen the soil itself supplies versus how much can be supplied via fertiliser, and in particular, can we use controlled release fertilisers to get a better synchrony between nitrogen supply and nitrogen demand from the sugarcane crop. Certainly in the sugarcane crop, where we've got, certainly in New South Wales, we've got a crop that might be grown for 2 years. We need to be able to supply nitrogen across that period. So when we were looking at the best ways to do that, these controlled release products certainly came out highest. Unfortunately, the years that we were doing the trials also happened to be the driest years in the last 50 years, and some of the results might not be typical of what might happen in an average year. So going to the title, the showdown. So I was trying to think, what was I thinking a year and a half ago when I wrote the abstract, showdown. And I typed into Google, showdown, and I got this cartoon, gunfight at the OK Corral. And then I was writing this talk on Sunday night, and I heard some cheering downstairs. And what's that cheering about? And I did another search, and I realised State of Origin was on. So I'm trying to make some analogies now between the results that I'm getting and some of the results that were shown on Sunday night. And I've also noticed that there's an absolute lack of maroon in the audience. So it came in on Monday morning, everyone was wearing blue or white, there's no maroon. Okay, so for accounting for the stocks in the sugarcane paddocks, there was actually very little, in New South Wales, very little information around how much nitrogen is actually there to start with. We do a lot of fertiliser trials, etc., but there actually is there's a paucity of information on what's there. So we took a whole stack of cores down to 1 metre, and we were having a look at a range of soil properties, including mineral nitrogen, and also potentially mineralisable nitrogen. And we used some of Diane Allen's methodologies for that, and we did PMN up to 450 days. So the types of tests that, as a farmer, you're not going to be using, because by the time you get the data back, your crop's already done and dusted. But certainly for our understanding of the nitrogen supply from the soil, it was important information. I've divided the data into 3 catchments. So the Clarence River, which is the furthest south in New South Wales, a bit further north around Ballina is a Richmond River catchment, and then the Tweed River catchment right on the border. And also what we've tended to find is that the soil texture tends to decrease a little bit the further south we go. So the Tweed catchment tends to be based on a lot of hydrosols and acid sulphate soils in the Tweed catchment, giving us quite low pHs, but also quite high organic carbon contents. And interestingly, on the Tweed sites, we're getting a lot of ammonium in the soil, so we're actually getting very little nitrification. And I think the low pH is almost acting like a natural nitrification inhibitor in those soils. Whereas the other sites, where the majority of mineral nitrogen was in the form of nitrate, as one would expect. I won't spend too much time on that data. So I'm just going to explain this graph a little bit because it's maybe a little bit complex to understand. Essentially what we have is just the number of field sites. We're just aggregating the number of field sites, and you can see there where the Clarence, Richmond or the Tweed catchments contribute to those field sites. And we're having a look at the ammonium content, the nitrate content, and a 14-day mineralisable nitrogen content in those soils. And this bottom graph, we kind of aggregate, we added all those together to see how much available nitrogen is potentially available in those soil profiles down to 1 metre. What's quite obvious here is that some of these sites, in particular in the Tweed, we've got a lot of available nitrogen prior to the crop being fertilised. One of the sites had 400 kilos of nitrogen available before the crop was sown, or before it was returned and before fertilisation. So, as a farmer or as an advisor, you go, do we actually need to apply fertiliser there? Is it actually needed? There are some sites with only 50, so clearly there is going to be a range of nitrogen responses there. And I would expect that those sites without much nitrogen will have a much stronger nitrogen response. Those with a lot more nitrogen probably have a lower fertiliser nitrogen response. And interestingly, when we had a look at the 300-day potentially mineralisable nitrogen, so that's the mineralisable nitrogen that would be more typical across a whole season of sugarcane growing, we had nearly half a tonne of nitrogen being converted into the mineral nitrogen forms. Now, I need to stress that this is a laboratory test, and what happens in the field might be a little bit different to what happens in the soil, in the field, the difference there, but it gives us an indication of the type of the quantum of nitrogen availability. So the next part of our trial was, again, to better synchronise nitrogen supply from fertiliser with crop nitrogen demand. So we ran 4 field trial sites in New South Wales, and we were having a look at the use of polymer-coated urea versus the standard practice urea. We used a polymer coat 90, so that the manufacturers were claiming a 90-day release of nitrogen from the polymer, and also then a blend of 90 and 270-day. One of the things that we wanted to find out was actually, are these polymer-coated fertilisers doing what the manufacturers claim they're meant to do? So upon discussion with some colleagues, we decided to use a bit like a litter bag type methodology. We planted, or we put the fertilisers into a control area where there was no other fertiliser applied, and we recovered them over a set period of time, up to 24 months. And what we were doing then is measuring how much nitrogen was retained in the polymer-coated fertiliser. We've got lots of data, but this is just some of the summary of the data. The blue line is from the polymer coat 90, and the maroon line is from the polymer coat 270. And they were probably doing pretty much what the manufacturers were saying they would do. So roughly half of the fertiliser from the polymer coat 90 came out within 30 days, and about half of the nitrogen fertiliser from the PCU 270 came out at 90 days, and there tended to be residual nitrogen in them, almost a year later, but only a small amount of residual. So they were probably quite accurate with what they were claiming. I guess the functions that control the release of nitrogen from the polymer are essentially temperature. So temperature is a key driver for nitrogen release, but I also think that there might be some component related to moisture and rainfall, probably to a lesser extent. And the key result there, PCU did what it was meant to do. So theoretically, we've now got a system where we can better synchronise our nitrogen supply to the nitrogen demand. Did that happen or not? Okay, so we tested this in the field using a rate trial. So some work that colleague Terry Rose from Southern Cross Uni did, having a look at a meta-analysis from a range of international studies using enhanced efficiency nitrogen fertilisers. One of the issues with a lot of the studies that we found was that we're either using the full rate of a polymer coat or an enhanced efficiency versus the full rate of urea to see the difference in emissions of nitrous oxide. Very few actually looking at agronomic performance. And those that do, there were a handful of studies showing that, in theory, if we start having reduced amounts of polymer coat or enhanced efficiency fertiliser, we can get improved yield or improved nitrogen use efficiency. So I guess the key outcome of that was that what we wanted to do is have a rate trial. So we matched urea content with the polymer coated urea across a range of different rates in our field study. I don't have time to present all of the field trial results, and one of the reasons I'm not doing that is that they actually all look pretty similar. We utilised the Cat Challenger for harvesting these field trial sites. Very accurate. I think the accuracy of that is to about 10 kilos when we're harvesting maybe 4 or 5 tonnes of biomass per trial site block. And yeah, it's just a pretty picture of the northern rivers of New South Wales. And this was a very typical response that we were getting. So we had our nitrogen rate, we had our 0 nitrogen added as per recommendations from DO and others. And we had our rate at 50, 100, 200, 300 and 400 kilos of nitrogen applied. The orange was a polymer coat and the blue was a standardised urea, and we couldn't statistically separate out the effects on yield or biomass nitrogen uptake at the majority of the sites that we tested. What was also interesting to note was that we had actually quite a flat nitrogen response curve at all of our sites. So the increasing nitrogen, even though at most of the sites it gave us a little bit of an increase in yield, it was only very, very minor. And then we applied Mike Bell's agronomic efficiency of fertiliser type calculation to this, and we had a look at our 4 field trial sites: Stotts Creek, Pimlico, Woodford Island and Coraki. And as one might expect, our agronomic efficiency goes down as we increase the nitrogen rate. The highest agronomic efficiency was with the lowest nitrogen rate, and at 2 of our sites, Woodford Island and Coraki, it was actually almost not different to our unfertilised control. So the key result, generally we had a flat nitrogen response curve from 4 of our field trial sites to increasing nitrogen dose. We struggled to separate out yield effects between the polymer coated urea or urea at matching end doses. Now, again, I need to stress that these are probably the 2 worst years possible, or 3 worst years possible to do a trial looking at enhanced efficiency nitrogen fertilisers, because there was no opportunity for nitrogen loss pathways. You know, it didn't rain, there was probably no, or there was no leaching, there was probably very little greenhouse gas emissions, and you know, we need to then question whether or not you know, it was a fair comparison in these two years. What we did find though was it was maybe a little bit of additional residual nitrate at a couple of the sites with the PCU. I mentioned earlier one of the problems with testing potentially mineralisable nitrogen, by the time you get the data, it's often too late to actually make a call in the, you know, an agronomic call for the farmer. So we ran some MIR calibrations across all of our sites, and we actually found, I think, a reasonable correlation between some of the MIR data and PMN at 300. So what we are now proposing is that maybe we can further evaluate this rapid test, very cheap, very rapid test, overnight test, for potentially mineralisable nitrogen, and use that to better, or to make better fertiliser decisions in the field, not based just on I guess, guesswork. We might be able to define what the mineralisable nitrogen might be. So, 2 key results. The soil N supply is a bit like the 2021 Blues team, somewhat dominant. So the soil supplied most of the nitrogen. And the polymer coated urea, I'm saying, is a little bit analogous to the Maroons in 2021, a bit ineffectual to yield across the 4 field trial sites. No tomatoes in the audience thrown at me, that's all right. But again, I need to stress that was because the years that we were doing the trial were actually not the best years to do enhanced efficiency nitrogen fertiliser trials. And maybe the funding model needs to be looked at as well. You know, are there better ways to do this work when when seasons are more inclined to give us the types of results that we need. I think I've pretty well stated all of these facts already. I think the next step will be a field evaluation of nitrogen recommendations based on nitrogen stock assessment using the mineralisable N calibration. I need to stress that calibration is for the New South Wales soils. If you send me a soil in from North Queensland or from a chromosol from Wagga, it's not going to work. It's very specific to the 3 or 4 soil types that we tested. Thank you.
Thanks, Lucas. I think we are running short of time because the next talk starts automatically, the virtual one. So if you have any questions for Lucas, you may email him. His contact details are there. Thank you. So the next talk is by John Baird. He's a PhD student and also staff at New South Wales Department of Primary Industries. He's going to talk on some N15 studies he conducted at ACRI.
Hello everyone, my name is John Baird. I'm a research agronomist with New South Wales DPI and a student within University of Melbourne. Today I'll be talking about my PhD study, which is within the More Profit from Nitrogen Cotton project. So the project is funded through the Australian Government Department of Agriculture, Water and the Environment as part of its Rural R&D for Profit program. It's also co-founded with CRDC, New South Wales DPI, CSIRO and the University of Melbourne. So today's talk is titled Quantifying the Seasonal Movement of Applied Nitrogen Fertiliser through the Use of Isotope Labelling 15N in an Irrigated Cotton System. So a little bit of background of Australian cotton industry. Predominantly cotton within production within Australia is irrigated and it's commonly grown on alkaline clay soils or self-mulching vertisols. And these soils are ideal for irrigation, especially during summer cropping, as they have a high soil water holding capacity, with some soils holding over 250 plant available water millimetres per 1.2 metres of soil depth. The average fertiliser application is roughly 350 kgs of N per hectare, and the recovery rate ranges from 20 to 40% of the applied fertiliser. Now, the recovery of fertiliser depends on a number of factors, including applied fertiliser rate, native soil fertility, cropping rotation and the product of fertiliser used. So there is a gap within the Australian industry in terms of the optimum NUE and the industry average NUE. So research conducted by Rochester et al. Has found that the optimum rate or index is 13 to 15 kgs of lint per kilogram of N applied. Whereas recent surveys over the last 5 to 10 years has shown that approximately 10 kilograms of lint per kilogram of N is being performed by the industry. And that's a gap that equals to 50 to 75 kgs of N fertiliser. So we have used 15N in an Australian cotton system before. McDonald et al. In 2017 found at end of season sampling and estimation found that atmospheric losses were the highest fate at 39%. Roughly 30% of applied N fertiliser was recovered by the plant, and there was 10% of fertiliser lost to the tail water. And so it was leached from the planting hill into the tail drain and lost from that field. So my investigation is really evaluating that that movement and that loss pathway and trying to quantify that amount through the season. So I conducted a field field investigation in 2018-19 with the application of 15N in urea liquid solution. It had 7% atom enrichment. Now the enriched fertilizer was applied down a 4-metre linear microplot, and each of those 4 metres were divided into 1 metre microplots. And the reason why was I had 4 sampling dates during the growing season. So those 4 dates occurred at first flower, early bulbs, cutout, and maturity. So I was really looking at that in-season movement of fertiliser N. So today, the investigation was built for 2 timings, 100% pre-plant and 100% in-crop. Today, I'll be focusing on the 100% pre-plant application, which occurred around 35 days before sowing. And the fertiliser was applied roughly 25 to 30 centimetres below the top of the plant hill. So this chart is my recovery at first square. So this is the fertiliser N recovery. It's not total N recovery, it's just a recovery at the NDFF. And this was early in the season at first square. And as you can see that the soil recovery equaled 85 kilograms of N fertiliser and the plant top was 33.5 kilograms of N fertiliser. So in combination, that was under the 90 kilograms of N fertiliser recovered, which was a drop of 60 kgs of the originally applied fertiliser. So I applied 150 kgs for this experiment, and I had lost 60 kgs of that fertiliser after 2 irrigations and at the very early in the season. Now, the plant of that 3.5 kilograms of N fertiliser recovered, the majority of that recovery was in the leaves at 2.5, and the stem was far less at 1 kilogram. And the fruit was developing, so it had very minor uptake of fertiliser N. But within the soil, there was significant difference in the location and the fate. As I said, there was 2 irrigations applied prior to this sampling. And just to highlight, so this is the irrigated furrow on the left, and as the waters infiltrated that planting bed or the plant hill, what we saw is that the nitrogen fertiliser really did actually predominantly rise from its application point to the top layers of the soil profile. And not only that, it moved towards the non-irrigated side of that planting hill. So there's very minimal to no recovery of fertiliser within this irrigated side, whereas all the recovery occurred either on top of the hill or across to the non-irrigated side of that planting hill. And this is a little bit changed. So the point of this is the fact that originally the BMP for the cotton industry is to apply the fertiliser deep and early, and which will minimise movement. But what this has shown is that the movement, even at applications at 20 to 30 centimetres below the top of the plant hill, we're still getting large movements, high movements, even after 1 to 2 irrigation events. So further into the season, so this is at early bulbs, just 1 to 2 or 3 bulbs on the plant, some flowers and some squares on top. What we find is the soil recovery has dropped significantly, the 24 kilograms of N fertiliser. Now, there was a storm event in between the first square and early bulb growth, so that could have contributed to that soil loss. But the recovery of fertiliser within the soil was really predominantly along that plant line still. So it's underneath the plant and above the application point. Plant top also had uptake of 55 kilograms of N fertiliser, and the majority of that uptake was driven by the leaf as the sink for that N fertiliser. The stem and fruit were similar in uptakes at this stage, but the fruit had increased significantly as well from early in the season. As we move further into the season to the cutout, what we found is that the soil recovered. We had similar recovery within the soil to the previous growth stage, but it had dispersed a lot more during that period, and we see a lot higher recovery on that non-irrigated side. So beforehand, the majority of recovery was within the plant line, and now we find a bit of a trend where higher recovery occurred on that non-irrigated high side of the hill, and also there was a significantly higher recovery down on that side and down in the furrow on the non-irrigated side. Again, like earlier sampling, we found minimal to no recovery of fertiliser at all on the third of the planting hill next to the irrigated furrow. So all recovery occurred either under the plant or on the non-irrigated side. In terms of fate of fertiliser within the plant fertiliser N increased to 60 kgs. And what we find now is that fruit and leaf are now have similar recoveries of N fertiliser. So during this second half of the season, the fruit uptake of fertiliser N has increased significantly. We see that the stem and leaf start to become a source of the N. So the assimilated N really is now moving from the plant tissue, vegetative tissue, across into that reproductive tissue. So this is the end of season, or at plant maturity. It was conducted when there was approximately 30 to 40% of open bulbs. So the bulbs down below on the plant were mature. We still had flowers, but predominantly the plant was filling the majority of bulbs it had retained. So as you can see at the soil, we've lost again a little bit, another 7 kilograms of N fertiliser since the last sampling date. But we found a lot more dispersion through that non-irrigated side. So there was more nitrogen recovered, fertiliser nitrogen recovered down on that non-irrigated lower side of the plant hill from that irrigated. Again, the plant line and the high side of the non-irrigated was significantly higher than all other locations, but there was a greater dispersion on that non-irrigated side. There was absolutely zero recovery on the irrigated side of the hill, and that was all the way up to approximately the high irrigation core site. So interestingly, within the plant, we didn't increase the fertiliser and recovery from the plant compared to the last sampling date. But what we found is from within the plant, there was assimilation of that nitrogen remobilisation of assimilated N from the leaf and the stem increased significantly again towards the fruit. So the fruit became the main nitrogen sink within that plant matter. So some key outcomes from this experiment. The majority of fertiliser N movement within the seedbed occurred early in the first half of the season, and particularly the first 3 or 4 irrigation events. So that's where most fertiliser moved and most fertiliser was lost. And the final fate of that the final fate of the nitrogen fertiliser was highly influenced on the irrigation infiltration, the amount and the direction within the soil. So that final fate within the profile was highly significantly influenced by the irrigations during the first half of the season. Later in the second half of the season and growing season, during the bulb fill stage, the leaf and stem provided the greatest amount of N to the fruit rather than from the soil as a source. So that assimilated N provided significantly more nitrogen to the developing fruit than what the plant would utilise from the soil. So that's interesting. As we move forward to higher yield and other timing ratios, whether that may change or whether a later in-season application may not be viable to improve fruit development. And finally, I'd like to say thank you. Thank you to my supervisors, Helen Suter, Graham Swanky, Ben McDonald, and Greg Constable, and also all to the staff at the field operations, the sample collection, and also the sample processing. Thank you. Thank you.
Straight away, you know his contact details. So the next talk is by Graham Schwanke, and he's going to talk on nitrogen mineralization in cotton.
Thanks, Gunnar. And how do I do this? This one? Yeah. Okay. Yes, so does excess nitrogen fertiliser affect in-crop nitrogen mineralisation from organic matter in irrigated cotton soils? So I guess what's the issue? Why am I up here talking about this? Well, the Australian irrigated cotton industry is very high yielding. It's one of the highest yielding in the world, and it's using a very high nitrogen fertiliser input to achieve those high yields. And previous work using 15N fertiliser recovery has shown that much of the crop and uptake comes from the soil organic matter that's been mineralised during the season. So I guess the question I had in presenting this is what's the impact of this high nitrogen fertiliser on the soil organic matter mineralisation? Is there an interaction there? And how to approach it? Well, you would have heard in John's previous talk and the next talk, and then there's 2 further talks later on this afternoon. We're part of a fairly big project, so we've got a lot of large paddock scale data to look at. We also have some lab scale attempts at trying to answer this question. So I'm going to go through probably too many results and then see if we can come up with any conclusions. So join me on the journey. So I guess just to help put things in perspective a little, here's a plot showing the increase in cotton lint yields in Australia over several decades. That's the orange line, and also the concurrent increase in nitrogen fertiliser being applied, and this data is from industry surveys. And the point that I've made with that green zone with the asterisk in it, there was a paper by Ian Rochester where he did a lot of calculations on nitrogen use efficiency and came to the conclusion that approximately 49 on average kilos of nitrogen was being applied. And you can see basically since then, since that study that he published, the amount of nitrogen fertiliser has increased by another 150 units of N, but the overall industry average yield hasn't increased a lot, and it's gone up a bit and come down a bit and bounced around a bit. So similar production, but a lot more inputs. So the first way I thought of looking at this was looking at some of our paddock trials, as I mentioned, and we had 4 years of paddock trials. Here's a photograph of one of them, and these 2 paddocks, in fact, and up the top paddock on the right there, we had one experiment within that paddock that was nitrogen by Pix by P. So we'll forget about the Pix by P part, there's just several nitrogen rates involved. And the approach that we're looking at is looking at the calculation for apparent mineral nitrogen. And it's a fairly simple calculation of nitrogen outputs minus nitrogen inputs. So we measured nitrogen outputs, as you can see on the left there, looking at the crop N uptake, and then we soil cored at the end of the season. We also measured runoff from each of the plots involved and looked at the nitrogen in that runoff. And in terms of the N inputs, we looked at the soil coring before the season. We know how much fertiliser we put in, and we also measured the amount of nitrogen in the irrigation water that was applied across the season. So this is a graph showing the 4 seasons and the 3 treatments in each season. So it's not a full nitrogen rate trial. It was never meant to be. We had a nil treatment. So we have the nil treatment with just the soil N and the amount of N in the water. And then you can see we had what I've called here a budget N treatment. Maybe not so in the first year, but in the next 3 years we looked at budgeting based on how much N was already in the soil and how much crop N uptake we expected, and just use a fairly simple calculation to come up with the amount of N that we applied. And then in each of the 4 years, we had a high rate, which was a high N fertiliser rate similar to the industry average, so around about 300 units of N applied. And here's some of the results in terms of the crop N uptake in each of those 3 nil, budget and high N rate treatments over the 4 years. So you can generally see there's an increase in the amount of N being taken up, except for that first year. Remember, in the first year, our budget N was actually fairly high. We didn't actually get to budget that year because the soil results didn't come back in time. And then in terms of irrigation water runoff, our nitrogen, as you can see from the results there, generally between sort of 10 and 20 kilos of N running off across the season. But in the second season they're much higher, particularly from the high N rate treatment. And the difference between those is partly to do with the paddocks involved and also to do with the seasons that we had. So, for example, in that second season with the high runoff, there was a fairly short paddock, and it was required a lot of watering to get the plant beds fully wet up. So there's a lot more runoff coming off in that season. In terms of the residual soil N at the end of those seasons, there was quite a bit after that first year in the budget and the high N treatments, but not excessive in the other years. So what did that all account to in terms of our calculation? Supposedly fairly simple for apparent mineralised soil N. Well, the nil N treatments, and in the next talk, Ben will talk more about these nil N treatments because he's explaining how we measured that in depth during the season in a lot of sequential coring. But here we're just looking at overall calculation. So our overall calculation is not that different from what we found in terms of the intensive coring during the season for the nil N treatments. And then you can see there's quite a lot of variation, particularly in the applied fertiliser treatments. And then, of course, there's some surprising things happening, particularly in the high N rate treatments. Apparent mineralisation is quite low or apparently negative in those last 2 years. So what's going on? It's a bit of surprise and a bit of a head scratcher, but I guess we have to consider the elephant in the room, and that's nitrogen losses that we're not measuring. And the chief one amongst those is denitrification. And that's been picked up in previous nitrogen fertiliser recovery, 15N recovery work as can be 50 to 100 kilos of loss there. So this calculation pretty much makes it very difficult to figure out what the mineralisation actually is and how it's affected by nitrogen fertiliser rate. So we didn't have a winner there. And just out of interest, I suppose, in terms of what the cotton yields were for those 3 treatments over the 4 years, you can see in none of the 4 years did adding the extra fertiliser N give us any extra yield. And in fact, in the last year, it actually decreased the yield. And again, that was in interaction with the season conditions that we had. So what's the next way I thought of looking at it was during another experiment, or taking some data from another experiment that we also had in the final year of the project, where we had a nitrogen by irrigation deficit experiment, but I'm only taking the information from one of the deficit treatments to look at here. So here are the treatments we had in that experiment. So again, we had the nil, we had the budget, and we had the high N rates, but this time we also threw in half of the budget N rate. So those are our 4 N rate treatments. Sorry, I'll stop this buzzing. So that's what we started with in terms of N inputs. So we're not looking at it in the paddock scale this time, but we took what we wanted to do was look at, well, what's really the key time for nitrogen mineralisation during the cotton season. So if you look at it when we're putting the fertiliser in, usually in these trials around September, planting in October, then you can see the green section of this graph is the N uptake curve, a stylised N uptake curve of the cotton plant, and you can see the N uptake rate needs to peak around that middle of summer, in the middle of January there. So we went out and took soil samples in the middle of January to see if we could pick some differences between the soils from those 4 nitrogen rate treatments. What we found was that obviously, as John has showed you in the previous talk, things change from irrigation, after irrigations in the season, in terms of after you put your fertiliser in, it doesn't necessarily stay where you put it. And here's the results of the ammonium nitrogen that we found in 2 depths, 0 to 15 and 15 to 30 centimetres, sampled in mid-January. And you can see that really only the high N rate had a lot of ammonium, or reasonable lot of ammonium still sitting in the soil. But when you look at the nitrate, levels much higher in terms of these concentrations. So there's really only a difference here between the nil and everything else, but also a difference with more in that topsoil. Again, as you saw it being concentrated in the topsoil, as John showed in the previous talk. So we've got those samples, and what we did to start with was look at a potentially mineralisable nitrogen index, which is an anaerobic 7-day incubation in the lab at 40 degrees. And I guess what we found from this, generally speaking, except for the high N rate samples, there was more mineralisation predicted from the surface soils, which is what we, I guess, normally find. That's where the more microbial activity is concentrated. But we can also, once again, see there's a negative thing happening there. So that's immobilisation occurring with our test. So again, we can't really sort of separate out what's happening in terms of the mineralisation, which we're most interested in. So then we went on to another way of looking at this, and as part of that, there was a aerobic soil incubation, again, lab-based at 29 degrees, both of these. This one. I should add, because that's the average soil temperature in that paddock in that time of year, as we previously measured. Again, a bit of a head scratcher. So whether we cumulated the mineralised N over 4 hours, 24 hours, 48, 96, 192, we got some pretty different answers every time. So where do you draw the line and stop? So if we stopped at 24, we thought, we've gotten some interesting mineralisation data here, but sometime in the next day, most of it got tied up, and that's not unusual for this soil, as some previous work by Ian Rochester, once again, has shown that nitrate in this soil is preferentially immobilised. So again, we've got our OLFO immobilisation sort of getting in the way. So what I tried next was looking at specifically trying to measure the gross nitrogen mineralisation process using a 15N pool dilution technique. And here you can see the results of that, fertiliser rate across the bottom and the mineralisation rate across going vertically, Again, some kind of weird results, and to help explain why they're weird, you have to think back to the soil ammonium results. So we're trying to dilute a pool of ammonium, which is really tiny. So the method really doesn't deal that well with pools that are less than 1 part per million, and most of them were less than 1 part per million, except for that deeper one at the higher N rate. And you can see it's well above 1, but there's a tremendous amount of variation. So we also looked at nitrification, as I said. I didn't say, but nitrification is quite quick in these soils, and the ammonium that was in the soils quickly converted through to nitrate. but we couldn't really detect any differences happening as a result of the pre-plant nitrogen fertiliser rate. I should add that we had to change the conditions for both of these 50N pool dilution techniques really to try and suit what we had, because we had a lot of nitrate, we had very little ammonium, and the ammonium that we did have disappeared within 4 hours, so that's why the ammonium one was only 4 hour. So I tried a range of things from paddock to lab and to right down to 15N individual process. Not sure that I really answered the question yet. So there may be some short-term effects with those high N rates, but I think there's an avenue here to continue this work. Where I started this thinking was reading some papers about long-term effects on mineralisation by continued high N rate use. And that, I think, is also worth investigating further. Thank you very much.
Thanks, Graham. There is one online question from Dave Lester. Any thoughts on link between cumulative water received, rainfall plus irrigation versus apparent N mineralization? Does amount of seasonal water correlate to soil N mineralization?
Sorry, Dave, you should have shouted it out a bit. It's a bit hard for me to read. What's a link between cumulative water received, rainfall and irrigation versus apparent N mineralisation? Yes, we did certainly see, in terms of the crop response, quite a lot of effect of our irrigation frequency strategies, so particularly in the last year. So we started out very dry. We had to put a lot of water in. In fact, this is one of the things that Ben will be discussing in his talk, the difference of irrigation strategies. So perhaps since I've run out of time, I better jump to... I'll talk to you outside as well, but yeah.
Thanks, Graham. We are moving into the next talk by Ben McDonald from CSIRO. It's a virtual talk. He will be talking on irrigation deficits on nitrogen, soil mineral N in cotton.
Hello, my name is Ben McDonald, and I'm going to be talking today on enhancing nutrient use in cotton production systems. This is a collaborative project led by the New South Wales Department of Primary Industries, the University of Melbourne, CSIRO and CRDC. Today's talk will be focused on irrigation deficit effects on soil inorganic nitrogen in alternate furrow flood irrigated Australian cotton production systems. A number of people involved in this work being Graham Swankie, Annabelle McPherson, Clarence Mercer, John Baird, Gunnar Natchamithu, and myself, Ben McDonald. So why is soil nitrogen mineralisation important, and why are we interested? Well, over the last 20 years of Rocky's field experiments conducted in fields 6 East and 6 West at the Australian Cotton Research Institute, we've seen on average between 100 to 200 kilograms of N per hectare being taken up by the crop in the zero fertilized treatments within his cropping rotation system. This shows that soil organic matter mineralization is an important source of crop nitrogen within vertisols. More broadly, when we look at 15N experiments, and this is work undertaken by Richard Bracken, where he's looked at 15N and also a range of other nitrogen experiments through the Australian cotton industry, we see on average about 100 kilograms of soil N per hectare is accumulated during the season. This contributes up to 70% of the crop nitrogen from the soil, which is derived from the soil. So it's an important component of crop nutrition in fertilized systems as well. When we look at the moisture content and temperature effects on mineralization, we see from Ian Rochester's work in 1991 that as we increase the soil moisture content and also temperature, we get an increase in the nitrate content of the soil. This work was done in laboratory experiments, so the rate of increase might be a bit greater than what we'd be experiencing in the field, but it's a fairly clear relationship. Conversely, when we look at denitrification, and this is work done by His Jamali, we see that when we change the amount of irrigation volume, we have a change in soil denitrification. So on one hand, in the mineralization side, we have effects of soil moisture on mineralization, and then on the denitrification side, we have a similar effect in terms of the amount of nitrogen lost. So we can see that potentially when we use soil moisture deficits to trigger watering, we could be deriving the soil nitrogen mineralization in different ways, and also denitrification in different ways depending on the level of soil moisture. The two graphs are the soil moisture traces for 2017-2018 experiment and our 2018-2019 experiment. We have two different deficits, and essentially the black circles are the lower deficits and the open circles are the higher deficits. We see there's certainly differences between the both treatments through the year. What does this cause in terms of variations in soil mineralization, and how should we take that into account as in terms of our fertilizer nitrogen calls? And this was the premise of the work. What is the effect of these deficits on soil nitrogen mineralization? So we conducted this work at the Australian Cotton Research Institute in Narrabri, and the station is out here on the Namoy River floodplain, and it's to the northwest of Narrabri. We looked at two cotton seasons, the 2017-2018 season, where we employed a 50 mil versus a 70 mil soil moisture deficit to trigger our irrigations. And again, in 2018-2019, we did a similar deficit irrigation treatment, but this time it was 60 versus 90. We had to change the soil moisture deficits because the increasing drought reduced our reduced our available irrigation water, and we needed to change what we were doing. One thing which did occur through the experiment is during 2018-2019, there was a hailstorm. And this hailstorm ran over the top of our plot and totally defoliated the crop itself, often breaking the main growing stem. And this artifact is throughout the 2018-29 season. Did a couple of things. One, besides defoliating the crop and breaking the main stem, it also resulted in the cropping season going for much longer than what usually occurs in a traditional season. So how did we set it up? So at ACRI, the cotton is grown in a mound furrow configuration where the water is run down the furrows during the irrigation, and the plant is grown in the hills or on top of the mound. The experiment itself was inside a broader, more profit experiment, which had multiple rates, multiple treatments. Here we're only looking at the 0N plots within this broader treatment. And we used 3 different replicates, which were sampled throughout the year, throughout the growing season. So at each of the sampling points, what occurred was a linear meter of plants was removed and collected from the sampling point. Early in the season, obviously there was not much plant to remove, but later, as the season progressed, the plants got bigger and more material was removed. At the point where, for example, where the red arrow is, we sampled the soil in the plant line pre-irrigation, and this was our time T. The irrigation then occurred, and then we waited approximately 7 to 14 days to then resample the plant line and take a soil sample. And this was time T+1. We sampled 0 to 15 centimetres and 15 to 30 centimetres. We measured the soil nitrate and ammonium in those samples. And then we looked at the net soil inorganic N accumulation within the soil between the irrigation periods, which is essentially the nitrate in the soil at time T, which we take away from the time T+1. We also measured the plant N uptake, which is essentially biomass times N content. And then from that plant N uptake, we can actually calculate what the mineralization was through the season by looking at what was the starting N and the soil and the finishing N in the soil, and using that equation on the screen, calculating the soil mineralization, which is NAP. We also did end of season whole plot measurements of yield, lint, and seed N. We used the GLS method to assess differences across the time series data, and we used the basic students t-test to look at differences between the end of season data. So what did we find? Well, in 2017-2018, there was a significant difference between the deficits. We saw a buildup of nitrogen in the 50 millimeter, which was much greater, significantly at the 0.5 level than the 70 millimeter deficit. In 2018-2019, again, we saw a significant difference, but that difference was driven from the last data point, which was collected in June. Otherwise, there was no significant difference at the 0.05 level. When we look at the plant N uptake, we don't see any difference between the plant N uptake in the linear meter, which was collected prior to the soil sampling. The 18-19 data on the right-hand side clearly shows the impact of the hailstorm on the crop in terms of the nitrogen which is accumulated over the season. But when we look at the data which was collected across the whole field plot for each individual N treatment, 0 N treatment, I should say, we see that in 17-18 we have significant differences in the cotton yield between the 50 and 70 millimeter deficit. We see more lint and seed N in the 50 millimeter deficit. And we also see a greater amount of plant N in the 50 millimeter deficit. In 18-19, we see no significance. So we think that what we've got here is in the 50 and 70 millimeter treatments in 17-18, because we're harvesting the whole plot, we iron out a lot of the variability which is hampering the, which was affecting the statistical analysis. We only look at the one linear meter. It is possible to use the plant N uptake minus the starting N plus the end of season N to estimate a mineralization in the soil of nitrogen. In 17-18, 18-19, we observed that more nitrogen was mineralized in the lower deficit, so the 50 and the 60 millimeter than the 70 and 90 millimeter. I can't tell you if that's significant or not because the way we collected the pre-season field N was not on a plot basis, it was on a field basis, and so we can't do that statistical analysis. But in terms of ease of method, this was much easier to do than going out and doing sequential sampling. Equally, we looked at the relationship, using the relationship derived from the Rochester and Bange 2016 paper, and we used the 0 N relationship here in this graph to estimate the crop N uptake. Again, we can use this to estimate the potential mineralization, or the mineralization which occurred over the season. Again, we can see differences between the 50 and 70 and 60 to 90. Can't statistically test those due to the way we sampled the pre-season. But again, this was a much easier method of estimating soil nitrogen mineralization than doing the sequential sampling. So in conclusion, we did see that soil N accumulation was influenced by the irrigation deficit. The measurement was difficult, and it is possible to use the estimation of N mineralised from lint yield or plant N uptake to make an easier estimate than going out and measuring the soil. Thank you.
Hello all. I assume you can hear me. So there's a question here from Lester around alternate furrow irrigation, and quite a good one actually. So the question's around if we alternate between each irrigation from the dry furrow to the previously irrigated furrow, would that reduce N losses? Potentially that could be a good solution for farmers to utilise to reduce the amount of nitrogen being lost through the system. Worthy of further work. Well, that's the only one there. There's one around from David Lester talking about the link between cumulative water received versus apparent N mineralisation. Did Graham deal with that one? That's all of it. Thank you. Unless there's any other questions. Thank you.